Thinking Aloud. Conversations on the leading edge of knowledge and discovery with psychologist Jeffrey Mishlove.
Hello and welcome. I'm Jeffrey Mishlove. Today we're going to look at the mystery component of reality. My guest, Dr. Edward Close, is the author of Transcendental Physics. He is also co-author with Dr. Vernon Neppe of Reality Begins with Consciousness, and he is the author of a chapter in a brand new anthology called Is Consciousness Primary?, edited by Gary Schwartz and Marjorie Woollacott. And the title of his chapter is The Mathematical Unification of Space-Time, Matter, Energy, and Consciousness. Welcome, Ed.
I'm glad to be here. That sounds like an interesting thing to talk about to me.
The mathematical unification, well, that's really your specialty.
Yeah.
And
yeah.
To begin with, when we think of the mystery component of reality, and in various sciences today, there are different designations for something mysterious. Parapsychologists use the term psi. In physics, we hear about dark matter and dark energy and things like gluons.
Right.
In biology, there used to be something called elan vital, and in martial arts they talk about ki and chi. So there's all sorts of designations in different fields of endeavor to refer to some mysterious but yet essential component.
Yes. And I've been told that the minute you mention the word mathematics, most people lose interest in what you're talking about. But I have a different take on mathematics. To me, mathematics is a reflection of the logic and structure of reality. And when we applied the mathematics, we made I think a rather significant discovery of something which is quantifiable, but it's neither matter nor energy.
And this is something you and your partner Vernon Neppe call Gimmel.
Yes.
And for benefit of our viewers who may not know, I have two previous interviews with Vernon Neppe regarding Gimmel. In fact, I'm going to post links to them. So people who are very interested, if you look in the upper right-hand corner of your screen right at this moment, there will be links to those two interviews. But you and Dr. Neppe, I think, are in fundamental agreement about Gimmel. However, you will express it in different language than he would.
Yes, Dr. Neppe and I got together because we were each looking for someone who was very experienced and very I want to say well-known, at least in their own circles, and successful in their circles, and with a high level of integrity to work together on what Vernon was calling vortical pluralism at the time, and what I was calling transcendental physics. And when we got together and started working on it, then we found we had a lot of epiphanies, but the one that probably, in my mind, is the most important discovery, and I really believe it's a discovery, was the discovery of Gimmel. Now, the big question is, how did that come about, and why do you call it Gimmel? Because if you couple the word mathematics and the word Gimmel together, many people will say, well, first of all, I don't know anything about either one of those things.
Yeah.
So what the heck are they? Well, how did Gimmel come about is maybe a good way to get into it. But it's not, interestingly enough, just a a theoretical notion or concept. It came about with the careful application, and this was my part in our partnership when we got together, was the mathematics and physics of it. Vernon's part was the neurology and the psychology and the philosophy and so forth. And not that either one of us doesn't know a little something about what the other does and thinks about, but we wanted somebody who's comfortable in those areas. So, because we're doing an integration of thought, of knowledge, and approaches to understanding reality, that we needed to integrate these things as very interdisciplinary. But for Gimmel, the way it came about was no accident in one sense, and yet it was kind of like Planck's discovery of the quantification of energy. He wasn't expecting that. Nobody was expecting that. Physicists certainly didn't expect that. But what did it turn into? It turned into quantum physics, and an important part of the technological aspects or applications of that are an important part of everyone's life at this point.
Well, in terms of quantum mechanics, it would seem to me ever since the term atom came into being in physics, the idea was some point you'd come down to an indivisible particle, sort of the basement, the foundation of all physical reality.
Yeah, and for the physicists at that time, it seemed like that basic unit or building block of the universe kept slipping through their fingers. It kept going down, down, down. And then they came to the quark, from the atom to the protons, neutrons, electrons, and then the quarks. They thought, well, that certainly must be the bottom of it. The idea that there's something missing in reality has kind of always been there in one way or another. But in our case, we thought that something, as I said, might be consciousness. But so for a long time, my passion almost had been to find a way to put consciousness into the equations of relativity and quantum physics. That was a goal of mine. But the way it actually came about was a bit of a surprise, like Planck's discovery, because I wasn't expecting it when it happened. And the way it happened was that we were looking at the combination of particles, starting with the quarks, the up quarks and down quarks, to form protons and neutrons, and eventually atoms, and eventually the reality we experience. And we, within the mathematical system that I had developed a few years earlier, I realized that there had to be a common unit of measurement, an equivalence unit. And kind of the key to that is we talked about E equals mc squared. Everybody knows that equation now. And it really is an equivalence equation showing the equivalence between mass and energy. And so that was kind of the beginning of the whole thing. And if we developed a unit, which I called first it was called like the quantum equivalence unit, and then linked it to empirical science. And I did that by looking at the elementary particles of reality and saying, which one has the smallest mass? So I started with mass. But then I realized the volume would have to be involved in this too. So did the smallest mass have the smallest volume? And nobody seemed to know an answer to that.
Yeah, we don't hear much about the volume of subatomic particles.
Yes, and part of that is, I believe, is the way they go about studying it in the Large Hadron Collider and all. This started way back with the cyclotron, or the atom smashers, as they called them, and the whole idea was to smash atoms with bits of atoms and break them apart and see what the pieces looked like, or what they acted like. So we were looking really at mass and energy mostly. We weren't looking at volume. We were looking at a sort of a cross-section of sort of a two-dimensional picture. And if you look at the things from the old cloud chambers, and you look at the pictures of the particles in even the Large Hadron Collider now, because the easiest way to display something is because you're putting it in the book is in 2 dimensions on a page. So you see the spirals and the particles, the tracks of the particles shooting off and everything, but you're really only looking at 2 dimensions of it. And but for the unit, the basic unit of a quantum mathematics, it had to be an equivalence unit that could somehow equate all of the different things that we measure.
Sort of the way we calculate atomic mass, I suppose.
Yeah. And there have always been efforts to do that, but even when Planck developed based on the quantum of energy and the equivalence of that with mass, that was fine. But then his, we call it a naturalized system. We don't think about it, but the units we use to measure things are just units of convenience. They're arbitrary. Could have been, an inch was, king somebody's thumb, the joint of the thumb, and a yard was from his nose to his extended hand or his thumb, and they were just, and a foot was really the length of his foot. So these were very arbitrary, but they were practical because they were the size that we could use. Well, when you get into the quantum world, you're talking about such a small size that feet and meters and quarts and gallons are not usable, because you wind up with fractions of that are hard to deal with. So they naturalized the system by setting the speed of light equal to 1 and setting other constants equal to unity. That sounds very abstract, but it's the same thing of setting this much equal, calling it an inch, calling it 1 inch. We call 1 kilogram or 1 pound or whatever. So it's arbitrary, so you can actually create a measurement system with any basic unit you want. So my idea was to tie it to physical reality and to the very intricate development of these measurements in the Large Hadron Collider. For instance, the electron, the mass of the electron has been determined in many, many different ways with great accuracy. So that was known. And among the elementary particles that form, let's just call it normal matter that we deal with every day, that makes up our bodies and our tables and chairs and everything around us, that matter, the electron is the very smallest mass of any of the elementary particles that make it up. Said, okay, that makes sense to me to naturalize the measurement to the mass of the electron. So that was a start, and I had all kinds of reasons for adopting the naturalization of the speed of light. That was done for practical reasons, because, as you know, the number of miles per second or meters per second is a big number.
Is naturalization the word you want, or normalization?
Naturalization. Now, there are two words, and that's a really good point. because normalization is when, let's start naturalization first. Naturalization is with particles, or with measurement, is when you set it equal to 1.
Mm-hmm.
That's basically what's a naturalized system. Mm-hmm. And Planck did it by setting the constants of gravitation and electrical constant and Boltzmann's constant, and 5 constants, all equal to 1.
Mm-hmm.
And well, in my system, or our system, you really only need 4, but if you're going to talk about mass, energy, time, and space. You need units of mass, you need units of energy, you need units of distance or time or space or volume, if you really want to look at it, not just a slice, but the whole thing, and time. And the unit of time and space relate to setting the constant of speed of light to 1, to naturalizing it. Now, the normalization comes about when you take the statistical data from the Large Hadron Collider, and you say, if I'm going to convert all of this to a quantum equivalence unit, it all has to become natural. It all has to become, in effect, 1. Start with this one with a basic unit. So when you look at it and you say, well, these are not integers. When you look at the mass of the electron, it's 0.511. That's a very, if you go 5 places, the others get very small. So that's very accurate. And if you look at the quark, it's 2 point something. If you look, in that unit. But now we've naturalized the measurement of the electron, so we need to convert everything else to that, just as if we would convert all lengths to inches or feet or whatever. Mm-hmm. So when we do this, we find that if the units are still not integers, not whole numbers, that they're still fractions, then we realize we don't have a quantum unit. Because quantum means you've got a unit that can't be divided further. So this was the whole job, was to set up a quantum equivalence system of units. And when we did, then the up quark came out to be 4 of these quantum equivalence units, converting it to the naturalized electron. And the down quark came out as 9.
Mm-hmm. In other words, this is a little surprising to me, because I assumed that quarks are the smallest possible things, and what you're saying is the up quark and the down quark are both much larger than the electron.
Yes. And in equivalence units, that's exactly correct. When we then had this quantum equivalence unit and we started measuring everything in terms of that, we found out that up quarks and down quarks added together should not give us a symmetric or stable third particle. This stopped me for a little bit until I thought about, okay, the way we have to overcome this problem is to look at combinatorics, another mathematical word, but meaning how we combine things. How do we combine how do we combine up quarks and down quarks to get a proton? And obviously it has to happen in a way that the proton is very, very stable, because it's probably the most stable thing in the universe. Protons just don't decay. They are very stable. So if you think about the fact that all of these particles are spinning, and most physicists will tell you we don't know why, we just know they're spinning. Well, to make a long story short, what we found was there was something missing. just like we were saying earlier, that every time there seems to be something missing when we try to understand the nature of reality. Mm-hmm. And what was that something, and how did we find it? We found that there was a quantity, an exact quantity that could be calculated of something that had to be in the mix with the quarks to form a stable, symmetrical stable. Now, if particles are spinning, what's one of the factors that would make it stable would be it has to be symmetric. If it's spinning and it's globular and irregular, it'll wobble and it won't be stable.
And they're spinning at very fast rate.
Very high rate of speed.
Mm-hmm.
And something spinning at that high rate of speed, if it's not symmetric, will fly apart.
We're talking about the spin at a speed maybe, a third of the speed of light, something like that?
Yes, at times, and in certain cases, even approaching light speed. Mm-hmm. And I could give examples of that, but the point is that when we got down to that point with quantum equivalence units, we couldn't have, and this was because of a well-known theorem called Fermat's last theorem. Mm-hmm. The way that works into the picture is a little complex in that it just eliminates one possibility of combinations. Mm-hmm. And we have to work to do that and get what are called Diophantine equations, which just means whole number equations. Mm-hmm. And if you're using quantum equivalence units that can't be divided further, then any description of reality using them will be in terms of whole numbers or whole units of the quantum equivalence unit.
Mm-hmm. Which obviously limits the potential solutions.
Yes.
To the equation. So you have to search for the next solution that gives you a whole number.
That's exactly right. This is what makes it a science rather than a speculation. This is what makes it real, because now it's tied to the mass of the electron and eventually the volume of the free electron. And everything's tied to that as multiples of that, and it works out wonderfully. Mm. But this missing thing, what is it? It can't be matter, it can't be mass. It can't be mass because if you add some more mass in, you no longer have an up quark or a down quark or a proton. You destroy the structure of that. You have something else, maybe a strange quark or one of the other 12 members of the families of quarks, which are very unstable and ephemeral. Mm. They quickly decay into up and down quarks. So what is this thing that makes things stable? We had to call it something, and we said, okay, we feel like if it can't be mass, and it can't be energy, which is an equivalence of mass, because if you put in more energy, you also destroy your quark, and you lose the stability and you lose the whole structure of the universe. So in order to have something rather than nothing, you have to have this mystery element that is in there that is neither mass nor energy.
So what we're talking about here is a mysterious ingredient that is required for reality as we know it to exist, because without this ingredient, particles wouldn't even hold together.
Right.
There could be no atoms or molecules because everything would be flying apart.
Yes, and if there was a Big Bang, nothing would ever get together. Everything would just keep flying apart and there'd be no universe.
It seems, in a way, analogous to the idea of consciousness in the Copenhagen interpretation. Everything is kind of a probability field until consciousness comes into the picture and you get what is known as the collapse of the wave function, or an actual observation of physical reality.
Material. Yeah, that's a very good analogy that works, because this something was there that makes everything stable, but it was neither matter nor energy. This is kind of analogous to, as you alluded to too, dark matter and dark energy, because most physicists will tell you we don't really know what it is. We feel like it has to be some kind of matter and some kind of energy, but it's not any kind that we know about. But the probes and everything to determine where it is, it's ubiquitous. It's everywhere in the universe. So it has to be a part of everything, and it's related to angular momentum or rotation, because that's how dark matter and dark energy were discovered, was by strange rotation of galaxies. So here we have a similar type mystery at the very opposite end of the scale, from galactic to regular to all the way to quantum. And the only other thing that human beings experience other than mass and energy and time and space is something we just call consciousness. Conscious being has awareness of the surroundings through the senses, but the surroundings are much greater than what the senses gather. So how do we, if we become aware of more and more, maybe we become aware of this something, this mysterious something, or maybe it actually has something to do with consciousness itself. It's the only other thing we experience. So really, Gimmel's a strange word, but we're talking about something that nobody knows what it is, but it's there and it has to be there. We determined mathematically and physically that it has to be there, but it's not anything that we know.
Well, you could argue, though, I'd take the argument a little more strongly when you say the only other thing besides matter, energy, space, and time that we experience is consciousness. Actually, we don't experience matter, energy, space, or time directly. All we experience is consciousness. Matter, energy, space, and time are inferences.
Yes, and that's why many people have come to think about consciousness as being fundamental to reality, if not primary.
Or if not everything. I've done many interviews with a fellow named Bernardo Kastrup who would say the entire universe is mental.
Yeah, and at one point I would say the entire universe is mathematics. But that's an abstraction.
Well, let's stop there for just a second, because if I understand the history of that idea, it goes back to Pythagoras and Plato. It has a very honorable tradition in philosophy to suggest that mathematics is at the basis of everything.
Yes, and if we actually can prove that this is the case, while using data from the Large Hadron Collider, tying it to empirical evidence about reality, then that's a big discovery.
As I recall, in Plato's Academy, at the very entrance, it said, "Let none enter here who don't understand geometry."
Yes, and that's an excellent observation, because what Einstein and Minkowski, the mathematician that he worked with, and several other people like Kaluza and Klein and Wolfgang Pauli and other people around the turn of the last century, the beginning of the last century, were looking at talking about geometry in terms of more dimensions. And that's what our model does too. So Gimmel is the third letter of the Hebrew alphabet. Why not use the third letter of the English alphabet? Well, because that's C, A, B, C. And
it's already been used.
Already been used for a number of things.
E equals mc squared.
Yeah, speed of light, Coulomb. It's been used for things. And if you go through the whole alphabet, both the English and the Greek, all of them have been used for something. I was favoring psi at one point, And Vernon said, no, people will, that's associated with psi phenomena or extrasensory phenomena, and that'll immediately get us in trouble with established science. So we've got to call it something else. So it became Gimmel. And over the years, I first discovered this in about 2010 or 11. But it was about 2015 that we decided to call it Gimmel. And from the beginning, I had strong intuition that we were talking about consciousness or an agent of consciousness, at least. And because of a series of equations that get us there that I call the conveyance equation, I saw it, or the conveyance expression that generates a number of equations, I saw it as a bridge, so to speak, from finite mathematics, or from mind even, to matter. Mm. And so more and more we begin to realize that it really can't be anything else but either an agent of or consciousness itself at that basic level of reality. Mm-hmm. Now the whole model begins to resemble other things like the perennial philosophy and many of the Oriental approaches, where they talk about consciousness being in everything. If this is indeed consciousness, then we've just shown that consciousness is in every particle down to the most basic one. And then an very interesting thing to me was when I thought, well, let's take this and apply it to the periodic table. Let's start. We've got quarks, and we know exactly, accurately, how many of these units of Gimmel, what we're calling Gimmel, have to be in each up and down quark in order for it to be stable and form a stable proton. Mm-hmm. So we can go from there. If we can determine how many of these units are in an electron, we can do the whole thing. We can do a whole atom. Yeah. If you are aware enough, and we talked earlier about consciousness expansion, mm-hmm. If your consciousness is not limited by the limitations of the physical organs of observation, but you begin to understand a broader, more comprehensive picture of reality, then indeed it's a easy movement from there to say consciousness is in plants and animals, and that there's a similarity. And if we really study consciousness, as Erwin Schrödinger, another famous physicist, who later in his life got very interested in biology, said that consciousness is only one thing. It's not a plural thing. Yep. It's the same in everybody. It's just that we're like a limited part as individual mm-hmm. consciousness or individualized consciousness. But if there's consciousness in everything, then we have a connection to everything. Yep. And we have a way of explaining phenomenon that we're studying, that people like Dr. Schwartz and Dr. Radin and others have been studying very carefully and proving by well-known statistical methods that some of these things actually do exist that we call psi phenomena. Mm-hmm. Here we have a way to explain it in terms that actually relate to things like the electron and the proton. The more we look at, even in string theory or any other theoretical physics model, we find that it turns out, as Max Planck said, there doesn't seem to be such a thing as solid matter. It's kind of an illusion that it's energy and maybe even consciousness. Planck himself even said that. So when we begin to put all this together, we see that if we have a science that's based on these quantum equivalence units that apply to the elementary particles, and by doing so we find that there is another element there, another component that cannot be matter or energy, then relating it to consciousness enables us to expand. It's a new a priori axiom, if you will, that expands our logical system from what it is in contemporary science to a science that incorporates consciousness and even what we've been calling paranormal. We're kind of, as human beings, we're in the middle of the spectrum, which is an interesting thing in and of itself. In a universe that stretches from galaxies to quanta, why would we happen to be right exactly in the middle? That almost says that our way of understanding and knowing things is somehow effective in what we know and what we see. If reality is quantized, and it's probably another whole discussion to talk about why we have to quantize time and space. Matter and energy, it's pretty obvious, I think. But if everything is quantized, then there are certain things that are not real, even though we can construct them mentally, and we can construct them with contemporary mathematics. This is why we need a new mathematics, where the basic unit is a volume and not a linear number.
Well, Dr. Edward Close, I think it's pretty clear that if for a person to really understand Gimmel, as you have outlined, that they have to take an extensive seminar with you. They're not going to get it from even a lengthy video like this. But if your theory is correct, it is incredibly profound and important for science and deserves to be carefully investigated.
Well, I thank you for that, and I totally agree. I think I really believe, because of that I've walked the path all the way from the electron's mass to the volumetric quantum equivalence unit, that I really believe that will eventually be understood. But it's kind of like you said about relativity in one of our other talks, that there were only 2 or 3 people in the world at one point that understood it. This is kind of the same way. It was the same with Newtonian calculus. There was actually a point in time where only a very limited number of people understood. Actually, I would say even today, even people who are in the science area or technology area may not understand the calculus. They just know that it works, so they use it. But if you ask them what are the asymptotic or what are the axiomatic basis for this whole thing, they just draw a blank. They just know that it works. So I would say even now, not everybody understands the calculus, and even now, it's still a limited number. It's more than 2 or 3, but a very limited number of people who understand relativity, and it's even a very limited number of people who understand the implications of quantum physics.
Well, and if I recall correctly, Newton himself was very unhappy with some of his theories in Newtonian physics because it implied action at a distance. Gravity, for example, that Newton didn't think should be possible.
Einstein, spooky Fernwirkung, spooky action at a distance. That was his problem with some of the things that come out of quantum mechanics, non-locality.
So going back at least as far as Newton, we've always had these mysterious aspects to reality. Well, Dr. Edward Close, a fascinating exploration. You're really raising, I have to call them head-scratching ideas, but I'm delighted to hear them.
Well, I really think that Gimmel answers a lot of questions.
Thank you so much for sharing your work with us.
Thank you so much for asking good questions.
And thank you for being with us.